And we'll do screen share. Mm. A plugin is required to share iPad. Okay, so maybe it updated and I need to install a plugin. Let's see if this fixes it. Okay, we should be good now. Okay, we're here. Cool. So let's just recall what we did last time. Well, okay, first, are there any questions that people wanted to ask before we begin? Anything? Nope. Okay, so let's just start last time. So, oh, that's green. All right, so now we have black pen. So last time, we talked about two different notions of indiscernibility. So we talked about S indiscernible trees. And these were trees where the language is LS, where you have the tree partial order, the lexicographic order, the meet function, and a series of unary predicates, alpha less than omega, which identify the levels in the tree. And then we had STR, indiscernible trees, where LSTR is the language of trees, where you have the tree partial order, the lexicographic order, a length preorder, and the meet function. And that's it. Okay, now both have the modeling property. So far so good. So they make sense to use indiscernibles indexed by these things. So here's the basic problem. So observation.
Nick? Nick?
Yeah, is there a question?
Yes. When you
What's
say
up?
that they both have the modeling property, you said last time that one of them is the one with the LS with the PNs. This doesn't follow from the theorem of Lin-Scow.
No, it doesn't, because the theorem of Lin-Scow had an assumption that a language is finite. But it follows from the theorem of Lin-Scow for any finitely many of them. So if you choose only finitely many levels, like an initial segment of the levels, then trees of height, of some bounded height in this language will be a Ramsey class, finite trees of some finite height, and then it follows from the theorems of Lin-Scow that you can find I-indexed indiscernibles based on them. Now, in general, the fact that you have the modeling property is about the consistency of a certain partial type, right? Where, what does the partial type say? It says that, like, whenever I have two things with the same quantifier free type, then the things that they index have the same type, and that you realize the sort of generalized version of the EM type of the collection of tuples you were given from the start, and that you can show by a compactness argument will be consistent if you know that it's consistent for the finite levels. So knowing it for the finite levels is enough to get the modeling property here, but it doesn't follow immediately from the theorem of Lin-Scow. Does that make sense?
Yes. Okay. Just another thing, maybe we use the trees of height omega. What
Yeah.
happens if you want higher trees? If you do,
Yeah, so we will, in fact. So when you do inisopy 1, you have to look at trees of arbitrary height. And there you can modify LS. So this is like LS omega. And you can change omega to any cardinal you like, and then add levels in indexing the cardinals. And again, because this really only boils down to stuff that you see at finitely many levels, if you know it for arbitrary finite height trees, then you know it for any tree at all. Because anytime you want to run this compactness argument, you only look at finitely many levels at a time, and you know that those have the right property. So like if you ever look at the Inisopy 1 papers where you do something like construct a tree Morley sequence, which is something we'll do in this class in, I guess, 2-3 weeks, you definitely have to look at S-indiscernible trees where the indexing set is huge.
Okay, thanks.
Yeah, no problem. Okay, so here's an observation that we'll start with. So suppose A eta in omega to less than omega, and phi x, y witness the tree property. So let's recall what that means. So I won't state the definition, but I'll draw the picture. So the picture here is I've got my tree of tuples, and if I move along a path, then that gives me a consistent partial type. And then there's some k, such that whenever I take a vertex or a node and I look at its immediate children, that gives me a k inconsistent collection of formulas. This is what it means to have the tree property. So suppose I have that set up, and additionally, I take some, sorry, not bi, but if b a eta in omega to the less than omega is S indiscernible, locally based on ai, sorry, a eta in omega to less than omega, then phi and b eta in omega to less than omega witnessed TP as well. I shouldn't say TP2, I should say TP as well, because TP2 has meaning. So let's think about why. Well, what do I need to say? So whenever I take a node in the tree, it's going to be at some level. So like this is like level 1, right? And whenever I take a node at level 1, and I look at k things at the next level that have that as their meet, I know that the things that they index are inconsistent. So you can look at a quantifier free type that says I'm at level 2. I have k things at level 2. Their pairwise meet is at level 1. And the things that they index are all inconsistent. Well, I should say that they're pairwise distinct as well. Well, I guess that follows from their meet being at level 1. Anyway, so that is going to be true no matter which k things I take, as long as their meet is at level 1, that the things they index is inconsistent. Since that's always true, that's going to be true of anything locally based on it. And that means that when I take something locally based, I'll have this kind of inconsistency. Likewise, when I look at, I don't know, any finitely many things which are on a common path, one of them at level I1, one at level I2, one at level I3, one at level I4, I know that whenever, as I move up in the sequence, like as long as I'm moving along a path, I get something consistent. That's going to be something true for anything of that quantifier free type, right? If it says like eta I1 is an initial segment of eta I2, is an initial segment of eta ... all the way up to eta IN, I know that the things that they index are consistent. That's true regardless of where they sit in the tree, as long as they're along a path. So that's also going to be true of something locally based. So if I start with a witness to the tree property, I take something locally based on it in the sense of STR, or sorry, in the sense of S indiscernible trees, then I get something which is still a witness to the tree property. Does everyone buy that? So this follows from the definition of local basedness using what you have to check. You have to check that paths are consistent. So you have to check that they're finitely consistent. And you need to check that children of a common node are k inconsistent. These are things which are expressed by formulas. And so they pass from the witness to the S indiscernible witness locally based on it. But this is not true for STR indiscernibles. Okay, why? Well, let's consider the following situation. Let's suppose I have a witness to 2 TP. So children of a common node should be pairwise inconsistent. Now, I know that paths are consistent, of course, but do I know, for example, that this and this are inconsistent? I don't, right? I don't know that because these are children of a common node. So these are not children of a common node. These are descendants of their meat, but the distance between these nodes and their meat is 2, not 1. They're not the successor of their meat. So the thing to notice is that, okay, if I look at this pair, so here and here, and I look at this pair here and here, so let's say this is A, and then B, B. These pairs have the same quantifier free type in the str language. Because what does the str language say? It says that they are incomparable, that the one on the left is lexicographically less than the one on the right, and that they have length bigger than the length of their meat. And that's it. So the str language can't distinguish between the case of when you take 2 incomparable nodes that are children of a common node and 2 incomparable nodes which are farther away from their meat, because you can't talk about the successor. You can't talk about at the next level. You just know that you're at some higher level. Does that make sense? This is something that you can't distinguish. So this creates a problem. So we have a fix for this. So a fix for this was the lemma from last time, which says that if phi is in TP2, then if A, well, let me say it this way. If phi witnesses KTP via the S indiscernible tree A eta in omega to less than omega, then then there exists some n such that whenever you have a sequence of n vertices such that 2 things happen, so that the length is constant, and also they have a common meet. So nu I meet nu j is equal to nu I meet nu I prime meet nu j prime for I not equal to j, I prime not equal to j prime. Then phi x a nu I less than n is inconsistent. So this we did last time. Now the idea was if you're in this situation here, let me just remember the idea. So you have your tree, and you look at a situation where, let's say you take nodes like this, where they really are children of a common node. Then you know that they're going to be inconsistent for any n bigger than k, because you assumed that you started with a witness to the tree property, in fact, of KTP. So these, of course, are k inconsistent. Now, if there was no uniform finite bound on how big the things at the next level were going to be inconsistent, so like if I took something here and something here, then in fact I could look at an array consisting of the nodes at that level as I move between this array, and I would get closer and closer and closer approximations to the tree property of the second kind, which contradict my assumption that I'm in TP2. So now, if I have this condition, then I know that when I take an str indiscernible locally based on a witness to the tree property, if my formula is in TP2, then it will still be a witness to the tree property. So let's say that. Corollary. If phi is in TP2 and witnesses KTP via the S indiscernible tree A eta in omega to less than omega, then there exists some in such that if b eta, eta in omega to less than omega, is str indiscernible and locally based on a eta, eta in omega to less than omega, then phi witnesses in TP via this new str indiscernible sequence. So maybe at a penalty of switching from k to n, I can assume that my witness to the tree property comes from an S indiscernible tree. So that's going to be really important for getting the configuration that we want. So now let's just go back and remember the theorem that we want to prove, because now we're finally ready to prove it. So the theorem says if phi witnesses the tree property, then T has TP1 or TP2. So just because I know it's really easy to forget these things, this is the one where it's incomparables are inconsistent always. And this is the one where you say you have an array where rows are inconsistent and paths are consistent. Okay, so this is just what we've talked about the last 2 times. Okay, so let's get our setup. So what we'll do is we will assume phi has in TP and is in TP2 and in TP is witnessed via the str indiscernible collection of parameters a eta, eta in omega to less than omega. So I have this collection of tuples, a eta, eta in omega to less than omega. Because I want to prove just the disjunction of TP2 or TP1, I can assume that I'm in a context where I'm in TP2. So I have an in TP2 formula which witnesses the tree property via some parameters. By the first remark, we can assume that that collection of parameters is S indiscernible. Because if we replace the A etas that were given with something locally based on them in the sense of S indiscernibility, it will still witness the tree property. So far so good. But then by the lemma, we could even assume that it's str indiscernible. Okay, so now we've got a very indiscernible witness to the tree property. And what we want to do is we want to extend that and show that maybe by changing the formula, we can find a witness to the tree property of the first kind. And just because I don't want to mess up the proof, I'm going to change this to k. Because of course, I mean, this variable has no meaning, but in my notes it's k, so I don't want to be confused, because this is actually kind of a technical proof. So I'm going to try to be precise, but I think like a reasonable approach to understanding what is happening is to just ignore the details and focus on the picture. Because if you understand the picture, then you'll understand the proof. And then it's very easy to get lost in the syntax. So let's get started. So we want a witness to the tree property of the first kind. So this is the one where we have a collection of tuples indexed by a tree, paths are consistent, and whenever I take any 2 incomparables, they're inconsistent. Okay, so first observation. Okay, so let's look inside our tree at the following collection of formulas. So we're going to look at A sub 0 to the I concatenated with 1, as I ranges over the natural numbers. So my claim is that this is inconsistent. So let's draw a picture. So sitting inside my tree, I've got the all zeros path. And then I can go up one, and then 0, up 2, and sorry, up 2 zeros and then 1, like this. So this one is like 1, and this is like 0 concatenated with 1, and this is like 0 squared concatenated with 1, and 0 cubed concatenated with 1, and so on and so forth. So clearly, these are all pairwise incomparable. And why are these inconsistent? So the proof of this will look a lot like our proof of the lemma from the last time. Because what we can do is we can look at an array. So what we can do is we can define an array. So let's say Aij is going to be defined to be A sub 0 to the I concatenated with J plus 1. Okay, so what does our array look like? Our array looks like this, 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 right? So it's like I go up the zeros path some amount of distance, and then I concatenate it with something off the zeros path. So all of these things are pairwise and incomparable. Okay, so this is an array, and by STR indiscernibility, Aij, ij less than omega, is a mutually indiscernible array. This is exactly, I mean, this is one of the things that the that tree indiscernibility will tell you, because as you move among these things, you don't change the lexicographic order relations that it bears with the other levels. You don't change its containment, I mean, its tree partial order relations with the other levels, because they're all pairwise incomparable. You don't change the meet. Any two of things at the same level will have the meet with all the others. So it's clear that these are mutually indiscernible just by looking at the relations that they have in the tree. Moreover, if I is less than omega, then phi x a I j. So now I'm fixing an I and I'm letting j vary. What is this? This is equal to phi x a sub 0 to the I concatenated with j plus 1 as j varies. Just unraveling the definition of our array. So this is like, if I go up to my picture, if this is level I, then what I'm doing is I'm looking at this collection of things and I'm saying, are these consistent or not? And of course, these are k inconsistent because these are children of a common node. These are all children of this node here. So, so this is k inconsistent. So by mutual indiscernibility, if phi x a 0 to the I concatenated with 1 as I ranges over the natural numbers, which is the same thing, as you recall, as phi x a I comma 0 in our array. If this is consistent, then phi x a I f of I less than omega, is consistent for all functions f from omega to omega. Okay, so what does this say? If I go back to the picture, this says, if I knew that this were consistent, then because this is a mutually indiscernible array, I would know that any way of picking something from each one of these rows is consistent because they're all indiscernible. So, you know, if I know this one is consistent, and this one is consistent, this one is consistent, then by sliding along the rows using indiscernibility, I can say that no, this one and this one and this one and this one is also consistent. So what did I find? I found this array where any way of picking one element out of each row gives me something consistent, but each row itself is a k-inconsistent collection of formulas. What is that? That's TP2. That means phi witnesses TP2 against our assumption. So we know that this is inconsistent. And so what was the goal? The goal was to prove that this collection of formulas is inconsistent. And we did that by showing that if it were consistent, then we would have a witness to TP2 with phi. Phi would witness TP2, and because we've assumed it can't, then this has to be inconsistent. Okay, so what does that give us? So what we can do, so what we'll do is we will let, and again, I want to stick to the notation of my notes because I don't want to screw it up. These will also be posted, so it could be useful. So what we will do is we will let m less than omega be maximal such that, okay, this is going to be weird, but bear with me. So we look at phi x a 0 to the I concatenated with 1 for I less than m union phi x, that's an x, a 0 to the I sitting between m and omega is consistent. So again, I'll draw a picture. So we've got the all zeros path. We take a maximal number such that if I take these things and then all of the elements of the all zeros path above it, that gives us something consistent. So like this together with this, and this is consistent. What does this look like? So this is like 1, this is like 0 concatenated with 1, dot to dot, all the way up to 0 to the m minus 1 concatenated with 1. What is the length of that? The length of that is m. So then here we start at 0 to the m plus 1, 0 to the m plus 2, and so on and so forth. So we want this to be consistent. Now, it could be that m is 0. And we know that if it's 0, then of course it's consistent because paths are consistent. So there definitely has to be a maximal m such that this is consistent, because if for every finite bit this is consistent, then of course the thing that we just showed was inconsistent would be consistent by compactness, right? So because we know that just the part where, like if I ignore this part, so let's pretend this doesn't exist for a second, and I just look at the part at the bottom, I'm looking at 1, 0, concatenated with 1, 0 squared, concatenated with 1, and so on and so forth. I know that this gives me something inconsistent eventually. So now I'm adding something else, and I know that that has to also become inconsistent eventually. So m definitely exists, right? There is a maximal m such that that's consistent, because otherwise the thing that we just showed inconsistent would be consistent. Okay, so that exists. So I'm going to undo that. Then what happens next? Then by compactness, there is some k less than omega such that, and again, I'm sorry, I know this is technical. phi x b 0 to the I. Oh, sorry, not b. This should be a. So now I'm looking at phi x a 0 to the I. Sorry. Yeah, 0 to the I concatenated with 1 less than m plus 1 is inconsistent. Okay, so what's going on here? Well, I looked at this picture here, right? And I knew that if I went up to m minus 1 concatenated with 1, 0 to the m minus 1 concatenated with 1, and then the rest of the zeros path, that was the maximal m such that that was consistent. So if I go one more, then it becomes inconsistent. So let's look at the picture. So I have the all zeros path. I go 0, 0, 0, 0. So here's 1, 0 concatenated with 1, 0 squared concatenated with 1. And then I go all the way up to 0 to the m concatenated with 1. And if I take the union of that together with this part of the tree, I know that that's inconsistent by maximality of m. So now I've gone one step further. I know I'm inconsistent. So that means that if I look at this formula, this formula, this formula, this formula, and then this infinite collection of formulas along this all zeros path, that's going to be inconsistent. So by compactness, there's going to be some finite initial segment whose length is capital K, which gives me inconsistency. So K is just this length that you have to go in this part of the path in order to get inconsistency. So that's K. Okay, so now we're going to change our formula twice. And so the first step is easy. We're just going to let capital, let's make it capital A, be this collection of stuff at the bottom. So this is A 0 to the I concatenated with 1 for I less than m. So these guys here are going to become A, just a name of the parameters. And then suppressing parameters from A, we will let phi prime x y just be defined by, you're going to have, so this is now in LB, where I have parameters from sorry, A, LA. So it's just going to be phi x, y, and this conjunction, I less than m of phi x, a 0 to the I concatenated with 1. So I just take the conjunction of instances, and I sort of treat it like it doesn't exist. So when I said I'm suppressing parameters from A, I'm just going to write phi prime xy as though it had no parameters. I'm going to treat the A like it's named with constants. But what is phi prime xy? It's phi together with the conjunction of these m formulas that were in the maximal consistent bit. Okay, so now what we have, so now we can rewrite what we had before. So what we know now is we can define A prime sub eta is just equal to A sub 0 to the m concatenated with eta which is still str okay for all eta in omega to less than omega. So then it's easy to check that A prime sub eta eta in omega to less than omega is still str indiscernible. And now str indiscernible over A. So what happened here? So we had our tree. And I fixed some nodes, right? Like these nodes here were my A. And now I just look at the whole tree where I only look at somehow the tree above 0 to the m in the old tree. Now, of course, that tree, if I take an in tuple of things here and I take an in tuple of things here, if these things have the same quantifier free type, then they all have the same quantifier free type over A, because they all sit in the same place in the tree order. They all sit in the same place in the lexicographic order. They all have greater length. There's nothing that you can say using A that would distinguish things inside this cone. So of course that's str indiscernible, and not just str indiscernible over the empty set, but str indiscernible over A, using the fact that the original tree was str indiscernible. So we have, so A prime sub eta, eta in omega to less than omega is str indiscernible over A. And now notice we can rewrite the inconsistency we had before. So we have phi prime x A prime 0 concatenated with 0 to the I, 1 less than or equal, less than or equal to I, less than or equal to K. So these are the K things we had. Okay, well, that's certainly true. Union phi prime x sub A prime 1 is inconsistent. Okay, I'm going to draw a picture. So what did we have before? So here we had our tuples from A, and then we knew that if we added one more, we were inconsistent with this stuff, right? So now in our new tree, the conjunction of this stuff has just been built into the formula. And if we take this guy, which is now A prime 1, together with the K things that were above it here, they were inconsistent. Unraveling what that means, it means that this is inconsistent here. So what have we done? We've just taken this collection of tuples along this collection of incomparables that we distinguished at the beginning, and we sort of built them into the formula. So no harm in doing that. Now we're going to use elongation. So what happens next? So defining B eta in omega to less than omega to be the k-fold elongation of A prime eta in omega to less than omega, and phi prime x z, where z is now going to be a tuple of variables, to be the conjunction over all I less than or equal to k of phi, oh, sorry, let me make this up psi. Psi. This is going to be the conjunction over these yi's. So z I'm understanding is this collection of tuples of variables. Then we have what? What do we have? We have psi of x b0 concatenated with 0, let's say, and psi x b1 is inconsistent. Okay, so why? Well, what does our elongation look like? Our elongation looks like this, right? The nodes in my elongation tree consist of like k tuples of nodes from the old tree. So if I look at here's 0 and here's 0, 0. So if I look at this node, let's circle it here. So I guess that looks like this. And then I look at this, then why is that inconsistent? Well, that's inconsistent because this guy on the right in particular includes this node, which is like the old one from before. And by indiscernibility, I know that this collection of tuples here has the same type as this collection of tuples here in the old tree. And in the old tree, this was inconsistent with this. So that means in the new tree by indiscernibility, this is going to be inconsistent with this. So in particular, these things are inconsistent using STR indiscernibility of the tree. And hence, sorry, I was right, phi, psi x b eta, psi x b nu is inconsistent for all eta nu with the following properties. So we have to think about which pairs now are inconsistent in our tree. So it's going to be all eta and nu with eta less than lexicographic order nu, and the length of eta greater than, or sorry, I should say it this way, use the language. So the length of nu is less than eta. Right? So again, I'm sorry, I know you guys are getting sick of me drawing pictures, but I'm going to keep doing it. So what did we see? We saw that if I went here and here, these were inconsistent. So what are the relations that hold between these things in the STR language? So it says that, so this is like 0, 0, and this is 1. What can I say in the STR language? I know that they're incomparable. So that's something that the language can say. Well, I guess I should say incomparable. Nu incomparable with eta. So I know that eta is lexicographically less. I mean, 0, 0 is lexicographically less than 1. And the length of 0, 0 is greater than 1. So on any such pair, I get something inconsistent because of STR indiscernibility. So notice that this is half of the battle, right? So now if I take two incomparables in my tree, either the lexicographically least one is smaller in length, or it's greater in length, or it's the same. So these are the three possibilities, right? So in the case where the lexicographically least one is higher up, I know that now those are pairwise inconsistent. Everyone see that? So now we just do the same thing once more. So now one more time faster. So now we do the same thing. Notice that the same argument gives that if I look at C, X, what is it called? I think it's B. So you look at B, 1 to the I concatenated with 0. I less than omega. Then this is inconsistent. So what am I doing now? So I have my tree. I have the all ones path. And I can go off it in the direction of 0 at any stage. So this is 1, this is 0 concatenated with 1, this is 0 squared concatenated with 1, 0 cubed concatenated with 1. All right, so at this point you might be worried like, oh, but like you assumed that phi was in TP2, not psi. And how do you know that this is true? Well, still, if this was consistent, then if you took the same array as you did before, that would contain the rows from before, as assumed, because now you have a conjunction of instances. So that array is going to be inconsistent row-wise for the same reason as before. Not just the conjunction, but actually each conjunct will be inconsistent along that row. So if these are consistent, then in particular, the formula phi is going to be consistent, and that will give you TP2. So this is going to be inconsistent for the same reason. And so you do the same thing. You take some maximal thing where it's consistent, and you make that a new collection of parameters B. And then you take an elongation to say that this is inconsistent with this elongated piece, and then you take an elongation and a conjunction of instances to get a new formula. So repeating gives a new formula, C, no, let's call it chi, x w, and str indiscernible tree, C eta, eta in omega to less than omega, such that if eta and nu are incomparable, and that their lengths are different. So let's just say that the length of eta is not equal to the length of nu. Then chi x c eta chi x c nu is inconsistent. Okay, why is this possible? Well, the tree that you built with already had the property that if you take two incomparables and the lexicographically least one has length greater, then they're inconsistent. So you preserve that property when you take conjunctions. So in the construction, when you do it the other way, now you know that if you take two incomparables, if the lexicographically least one has length greater, then they're inconsistent by the previous construction. By the outcome of the new construction, if the lexicographically least one has length smaller, then they're inconsistent. And then so now you only have to worry about the case when they have the same length. So what do you do if you have the same length? Well, here is a kind of stupid trick that you can do. So then, to finish, let mu x u be chi x w0 and chi x w1, and let d eta, eta in omega to less than omega, be the twofold elongation of c eta, eta in omega to less than omega. So what happened here? So we started with this tree, and then we took our twofold elongation to get this new tree, right? So now the thing to notice is this and this are inconsistent now. Why? Well, because in the old tree, this guy and this guy have different length. And I knew that if I had incomparables at different lengths, then they were always inconsistent. So if I just do this thing where I replace each tuple with its twofold elongation, then I force that whenever I have two things at the same level, they contain subtuples from the old tree that are at different levels, and so they're inconsistent. So now, for all eta incomparable with nu, mu x d eta, mu x d nu is inconsistent. We maintained consistency of the paths. At each stage. So mu witnesses TP1. And that's the proof. Okay, so this comment about preserving paths, this is why we did this thing that might have struck you as a little confusing at the beginning here, where we assumed that this whole path was consistent, right? We didn't just look at how many of the the zero concatenated ones we could take that were consistent. We actually looked at the number of zero concatenated ones we could take that were consistent with the whole path. Why? Well, because we wanted to know that if I looked at this formula and then I took instances here and instances here and instances here along this path in my new tree, that they were still consistent. Why are they still consistent? Well, because I took them so that they would still be consistent. That M was chosen so that I could still go up. I could still take paths. So I know that this proof is super confusing. I think it's one of these things that it's really hard to see. But my main goal was to show the basic operations that you do with the indiscernible sequence. So you can do things like shift up and look at the tree above a particular node. That of course preserves an STR indiscernibility. You can take elongation, replace your formula with conjunction. That will still preserve much of what you care about. And using this over several changes of tree and several changes of formula, you can pass from a witness to the tree property to a witness to the tree property of the first kind. And that's the theorem. So you see that it's harder. It's harder when you work on trees. So this is a much more difficult theorem than the proof for strict order property or independence property, but it's a similar idea, and it's the proof is really, well, I don't know. I quite like the proof, so I'm happy to share it. Okay, so I think that's it. Are there any questions? No? All right, so I'll stop recording.